Okay, we study X4, rotation and cross product. Describe how to compute the scalar product. We have a two-dimensional Euclidean space. We first choose the x and y axis of the Cartesian axis, and we rotate this one by an angle theta. So we have x prime in here and y prime there. We'd like to know the scalar product among these four unit vectors. We recall that EI dot EJ in a single coordinate system is canonical delta IJ. They are either 1 or 0. If two indices are the same, it is 1. Two indices are different, it is a 0. However, if I make a rotation and to find out the scalar product between any two unit vectors, it is because the magnitude of each unit vector is 1, is cosine theta, where theta is the angle between the two. Let's see. Determine the angle psi between EI and EJ prime. That is the angle between these two. It depends on these indices. Let's see. Angle between E1 is here, E1 prime is here. The angle between these two vectors is theta. Therefore, it's trivial to find that this scalar product E1 dot E1 prime is a cosine theta. In a similar manner, we can find the scalar product between E2 and E2 prime. They make angle theta. Therefore, the scalar product between these two is cosine theta. Okay? Next, we consider the angle between E1 and E2 prime. Where is E1? E1 is here. E2 prime is here. We have a right angle, and the angle between these two is half of pi plus theta. Cosine half of pi plus theta is a sine, negative, so minus sine, okay? So simple way to remember is if there is a half a pi, then you remember a right triangle. You have theta here. This is cosine and this is sine. If you look for the angle in here is a half of pi minus the theta, because the sum of the all three angles is a pi in any triangle. Therefore, if it is a right triangle, theta exchange of theta and half of pi minus theta exchanges cosine and sine. In addition, you need to consider the sign difference if it is possible. If they are on the same side, cosine is always positive. For example, cosine is a positive if they have a parallel component along the same side. If the angle is greater than half a pi, for example, these two, cosine becomes a negative. They are in opposite direction, okay? As far as the parallel component is concerned, this arrow, these two arrows are opposite direction. So just find out the parallel component of this from this, you can find they are opposite. If they are opposite, then you need to put the negative sign on it. Therefore, E1 and E2 prime, we have a right angle, so we have to replace the angle cosine with sine, and if in this case they have opposite direction, opposite parallel component, so we have negative sign on it. Easy to remember. And then next we study E2 and E1 prime. E2 is here, E1 prime is here. This is theta, this is right angle, this is half a pi minus a theta. Aha. So in this case, the angle is less than, smaller than half a pi. So I flip cosine with sine, and we do not multiply negative sign on it. So simply it is a sine. Express E1 prime, EI prime in terms of EIs. Primes are here and there. First of all, we consider this. To go ahead, we need to know what the completeness relation is. That means it is a trivial. Any vector on a plane is a linear combination of two unit Cartesian basis vector. And its coefficient is called A1 and A2. They are Cartesian components. Any Cartesian components can be obtained by taking the scalar product with a unit vector along that axis. A2 can be obtained by taking the scalar product with the unit Cartesian basis vector along the y-axis. As a result, any vector, this is A, you can substitute B, whatever. Anything on a plane must be something dot 1 E1 multiplied by E1 plus something dot E2. In this manner, it is called the completeness relation. Why do we say completeness? We don't miss anything. Any vector on the plane can be expressed in terms of two Cartesian coordinates. You learned in high school already. If I extend this one in the three-dimensional space, this one can be expressed as a vector is A dot E1, E1, A dot E2, E2, and then A dot E3, E3. So this is completeness relation in three-dimensional Euclidean space. Anyway, so applying this completeness relation, whatever E1 prime in here is a linear combination of E1 and E2. What are the coefficients? They are scalar product with 1, 1, 2, 2, okay? E1 prime, I'd like to express E1 prime in terms of E1 and E2. Then coefficients are E1 prime, that E1, E1 prime, that E2. And actually, we can copy our previous result. Where is it? This one, E2 dot E1 prime. Aha, E2 dot E1 prime. I know this. This is sine theta. And where is it? E1, E1 prime. I can copy this result. This is cosine. Copy this result, cosine. I wrote in this way. By the way, this is nothing but the structure. This one has the same structure as some scalar product. In the previous class, A dot B is expressed as A1, B1 plus A2, B2 in the two dimension. This one can be expressed as A1, A2, and B1, B2. Why don't we rewrite this in a matrix form. Then cosine sine, I copy the coefficient, and this one, why don't you stand up? 1, 2. Okay, this matrix multiplication form for the scalar product can appear in the expansion of E1 prime in terms of E1 and E2. In a similar manner, I can expand E2 prime in terms of this guy and this guy. Again, I apply the completeness relation, E1 plus E2. What are the coefficients? 1, 1, 2, 2. Copy this one in here and there. Okay, so I need to copy this. Where's the multiplication table for E2 prime and E1? E2 prime and E1, I can copy this minus sign in here. And then E2 prime, E2. Where is it? This guy, they are cosine theta. Cosine theta. So copy this result to find that I have something E1, something E2. Again, write down the coefficients in order, cosine, and why don't you stand up as a column vector E1, E2. As a result, I have this guy and this guy. Why don't you copy this order by order? First one, first column, and this first row. Okay, E2, second column, second row, and this copy as a second row. And they are common factor. Standing up, they say they are the same. Okay, so in this manner, I can write these complicated expressions in a very compact form. So this is due to the introduction of a Cartesian coordinate system. So we have to thank Descartes for introducing this very simple idea. Thank you, Descartes. So next, we would like to find how to write a vector that is identical to the original vector in magnitude. So this is a circle. However, this primed vector has a different direction. It is obtained by rotating this original vector counterclockwise. Your clock is rotating in this manner. It is clockwise. But usually we are representing the direction of a general rotation counterclockwise, not clockwise. So if I rotate any vector A counterclockwise, what happens? That is my question. It's an extremely important part. So I copy a previous result. If I rotate the basis vector from in here by angle theta counterclockwise, primed basis vectors are expressed as a linear combination of unprimed basis vectors. Suppose that I have an original vector A in terms of original basis. What happens? It's a coefficient Cartesian components A1 and A2. Okay, write down as a matrix product form for the scalar product style. Copy the coefficients that are the Cartesian components of original vector. And why don't you stand up as a column, and then these are the unit basis vector of the original coordinate system. So that's fine. And then why don't we rotate this? In that case, there are two ways of representing this rotated vector. One way is keep these coefficients the same and then just put the prime because we have this one is A1 and this is A2. So we have a right triangle A1, A2, and vector A. Okay? We would like to rotate this one in this manner, and we have a prime vector. The length of these two sides must be the same even after the rotation. So we remember this is along the E1 prime direction, and this is along the E2 prime direction. So we can make use of primed basis vector after rotation. Then you'd rather use the original component that should be invariant. So this is one way to write down the rotated vector. So if I follow that way, and we always copy previous result, copy our result in here. This is identical to this. So I substitute this one for the standard version column vector of the primed vector. So this one has been copied in here. Okay, I have inserted a matrix, and then you remember A dot B equals B dot A. A dot B dot B dot A. What's that? A1, B1, A2, B2, A3, B3. That is B1, A1, B2, A2, B3, A3. What's that? This is a B1, B2, B3, and why don't you stand up? A stands up. This is identical to A1, A2, A3, and B1, B2, B3. Why? Why? Scalar product is commutative. As a result, we exchange, what's that? Just let it stand up. If this guy stands up, they exchange the order. Therefore, exchanging this version and this version is called transpose. Why don't you stand up? Why don't you lie down? Okay? So column becomes row, and row becomes column, and exchange left and right. This is called the transpose, and that is possible because the scalar product is commutative. Therefore, okay, why don't you lie down? Why don't you stand up? Okay, stand up. This guy, stand up. All right? This is called a transpose, and transpose does not change anything about the scalar product. As a result, what we have found in here is a linear combination of this rotated vector as an expansion of original basis vectors. We can say the new coefficients for the original coordinates. Let's see. This one, this guy A1, A2. Original components in terms of original coordinates. After rotation, this vector has a different x component that is called a1 prime, different y component that is called a2 prime. So these one new components in terms of old original basis vector called E1 and E2 that we are interested in. As a result, this one can be copied directly from this one. What's that? I copied this and copied this. This is our final result. It is very, very important. Very, very important. Okay? You have to memorize. Next, we consider cross product. Cross product is defined by the product of magnitudes and sine of angle, and there's a unit vector n hat that is perpendicular to this plane spanned by A and B. By using right-handed screw law, we choose n hat unit vector perpendicular to this plane, but if you use your right hand, swipe from A to B, your thumb is heading toward the n hat. Okay, so you have to distinguish what is n hat and what is minus n hat. You can make a mistake if you are not careful. And then, because of this sine theta, if there are two vectors parallel, angle becomes 0 and sine becomes 0. So this one vanishes. And we know we'll have angle theta and A and B. What is that? Area of a parallelogram is represented by A times B sine, because A sine theta is the height and B is the base. Base times height is the area of a parallelogram. So this one, magnitude of a cross product is the area of a parallelogram spanned by these two vectors, and direction should be chosen in this manner. As a result, cross product multiplication table is quite simple. What's that? 1, 1, 2, 2, 3, 3. If they are the same, cross product becomes a 0. They survive only if they are perpendicular to each other. Okay, 1 and 2 are perpendicular to each other. As 1 plus 2 is 3, and 2 cross 3 is 1. 3, 1 equals 2. However, remember, if we exchange these two, you have negative sign on it. A cross B is equal to minus B cross A. As a result, 2 cross 1 equals minus E3. 3 cross 2 equals minus E1. 1 cross 3 equals minus E2. In this manner, among the 3 times 3 equals to 27 expanded terms, only 6 of them survive. 6 of them survive. Why? 1, 2, 2, 1. 2, 3, 3, 2. 1, 3, 3, 2. Okay? 1, 3, 1, 1, 3. So 3 times 3 times 3, 27. But among them, 21 die. Only 6 survive. And among them, they are 3 by 3. The 3 cases are positive. 1, 2, 3, 2, 3, 1, 3, 1, 2. And 3 guys, opposite, negative sign on it. So 6 is actually 3 times 2 times 1. That is called the 3 factorial permutation of 3 indices. And in here, we have 1, 2, 2, 1, 3, 2, 2, 3, 3, 2, and 1, 3, 3, 1. 6 permutations, and then what happens? What happens? 1, 2, 2, 1, they are opposite. 2, 3, 3, 2, opposite. And 1, 3, 3, 1, opposite. They have negative sign on it. Because of that, A1, B2, A2, B1, A2, B3 minus A3, B2, A3, B1 minus A1, B3. So negative sign appears. And all these guys are expressed in terms of 1, 2, and 3. Finally. So in the end, cross product survives only if they are the same. We have 3 factorial cases. As we know, they have 1, 1, 2, 1, 2, then it's parallel to 3, 2, 3, it's parallel to 1, 3, 1, it's parallel to 2. As a result, we can define the triple scalar product, that is a cross product of 2, and then take the scalar product with the other. This is nothing but the volume of a cube when I, j, k are all different. 1, 2, 3. If you choose these 3 axes, any 2 of the axes are the same, this cube becomes like that, or like that, straight line, 1, 1, 1. This is a rectangle, it's a square. Only if all of these indices are different, we can make a non-vanishing volume. Volume survives only if these 3 indices are the same. They are 6 permutations, and the 3 permutations are called even permutations that have positive sign on it. And we have exchanged these 2 to find 2, 1. Exchange these 2 to find 3, 2. Exchange these 2 to find 1, 3. They have opposite sign on it. Therefore, we call it odd permutation. So 6 permutations consist of 3 even permutations and 3 odd permutations. Remaining pieces, 21 pieces, are all vanishing. And we call this triple scalar product to be the Levi-Civita tensor. And Levi-Civita tensor. And I hope you visit here. You know what this place is. And in ESA in here, this is more detailed explanation about the Levi-Civita symbol. And it is a very, very, very useful for your future. So I hope everybody must study. Okay, I told you the Levi-Civita symbol is well explained in M1 in the Escape from Scientific Absurdity C series in M1. Click here to find that. All right. This is how to find the area of a circle. Area of a circle. And on the 2-dimensional plane, you can introduce the radius and angle. Radius and angle to define a point on a circle. You change this circle of radius from 0 to capital R. And this is the way to find out the area by integrating over the radius and angle. You will find a way to find out the area of a rectangle whose radius is from r to r plus dr, and the angle is between theta and theta plus the d theta. And you will find these two sides, radial side and tangential side, and find out the cross product to find out the area of this tiny area, and take the infinitesimal limit and sum them all to find out the area to be pi r squared. So it is a very straightforward, and what we have made, what we have derived for this cross product and the scalar product, the triple scalar product, will be very useful to reproduce all of the result. Okay, that's it for today.